acyl chloride. So 9.1 preparations of acyl chloride. Okay, you have carboxylic acid. You look at the chart here, carboxylic acid. You want to change it to acyl chloride. The first way, you use PCl5. PCl5. PCl5, we learn it in the AS alcohol, where the OH is replaced by Cl. So likewise, same idea over here. The OH of the carboxylic acid is replaced by Cl. So it form RCOCl and plus, actually this is plus, RCOCl plus POCl3 and then plus HCl. Okay, so you can refer back to alcohol to understand all this. Okay, that time I already mentioned how they react in details. Okay, so the second one, RCOOH plus PCl3. So they form RCOCl. Again, the Cl replace the OH. And after that, they form, okay, this thing is not clear enough, it's plus, then H3PO3. Okay, so this is the phosphorus acid. Now, next one, carboxylic acid react with SOCl2. This is thionyl chloride. So that we form RCOCl plus SO2 plus HCl. Okay, so what we can see here is the OH is replaced by Cl, and that product is called acyl chloride. Okay, so acyl chloride is RCOCl. Okay, so anything special about RCOCl is it is very reactive. Very reactive. Why? Because of the carbon, which is very positive. So oxygen is withdrawing electrons. Chlorine is also withdrawing electron, making this carbon have delta positive, that is more positive. And nucleophile could easily come here to attack this carbon and making it very reactive. Okay, so now let's see the first point. These are derivative of carboxylic acid. OH group of acid replaced by Cl. OH replaced by Cl. Named after corresponding acid using suffix oil followed by chloride. Example, this is ethanoic acid. So it becomes ethanoic chloride. Ethanoic chloride. The structures is like this. So 9.2, reactivity of acyl chloride. Very reactive, of course. So acyl chloride is also called acid chloride. Much more reactive than the carboxylic acid, from which they are derived. So if you are comparing ethanoic acid and ethanoic chloride is much more reactive. Next point, polarity of both CO and CCl. CO and CCl. What happens? CO, the O attract electron. The Cl attract electron also, making this very lack of electron very positive. So polarity of both C double bond O and CCl bond produces relatively large delta positive charge on the carbon, making it electron deficient and more susceptible to attack by a nucleophile. Okay, so nucleophile will easily come to the carbon and react with that carbon. So let's look at the next page, 9.3, nucleophilic condensation mechanism. Okay, so what happened here is the nucleophile attack this carbon, they form a new covalent bond. So the double bond of the oxygen becomes single bond, and after that they will take negative charge as the electron from the double bond go up here and become negative charge. Okay, so they form a new covalent bond, and after that, to stabilize back the situation, the X have to be removed, the double bond is reformed, and now X minus is disappeared already through heterolytic fissions, and then this is the new product. It's basically Cl replaced by the nucleophile. Okay, now the carbonyl carbon being highly electron deficient, it refers to this carbon, is attacked by nucleophile. The nucleophile bond to the carbon atom. The C double bond O bond is broken, leaving O with negative charge. You can see that, negative charge here. Chloride is lost and carbonyl double bond is reformed. So you see, it's single bond, after that become double bond again. And the X minus come out, that is the chloride. Chloride will just go away. Okay, now let's look at 9.4, nucleophilic condensation reaction. So just now we already understand the mechanisms where nucleophile attack the carbons, that is very positive, and then the X minus come out. So the X minus will normally come out and form HCl. So the productions of small molecule like HCl is known as condensation. Condensation reaction either produce H2O or HCl. Okay, so the first reaction here, hydrolysis. So for hydrolysis, acyl chloride react with acid in aqueous. They will form H2O. Oh, sorry. This is not the product. This is the reagent. So acyl chloride react with water in acidic conditions. Then what happens is the OH of the water is the nucleophile. They will come and replace the Cl by going through the same mechanism like in the previous page. So Cl will come out, OH will go in. So Cl come out to form HCl with another H coming from the H2O. So the H come from H2O combined with the Cl minus that come out through the mechanisms and form HCl. So removing of HCl is a condensation reactions, and the nucleophile will remain, the OH is the nucleophile. The OH form, OH stick to the carbon. So they form this product, which is carboxylic acid. If you use hydrolysis or alkaline hydrolysis, so you have to use NaOH. So NaOH will produce the OH minus. The OH minus supposed to replace the Cl to form carboxylic acid here. But the thing is, after forming this carboxylic acid, right, it will further react with NaOH again through neutralization to form salt and water. So that means it is good if you take it in two steps for this case. For this case, the first step is RCOCl plus NaOH. So initially they form RCOOH plus NaCl. This is number one. But the thing is, RCOOH is acidic. The surrounding is NaOH. So that will neutralize to form RCOO Na plus plus H2O. So that's why there are three products. NaCl, RCOO minus, Na plus, and H2O. So there are three products. Okay, so it is easier to think about it. It is easier to think about it in two steps. The first step is similar to the acidic hydrolysis. Then the second step is neutralization. Okay, now the next one is forming amide. So what is amide over here? So this amide is C double bond O and H with something else. That is amide, the basic structures of amide. So in order to form amide, now let's see. Your Acetylchlorite react with NH3. The nucleophile here is the one with lone pair. So it's NH2 of course, NH2. So the NH2 will stick to the carbon. Cl will be removed and combined with another H that remains. It forms HCl. And the structured form here, this structure, is called primary amide. So what is primary amide and what is secondary amide? So it depends on how many R is there. So this is 1R, primary amide. Secondary amide, of course, you should expect 2R, you can see here. R on the left and R prime on the right. So this is secondary amide. You can see 2R on the CO NH structure. So if you want to form secondary amide, you have to use LQ amide. Okay, LQ amide. LQ amide is actually what? It's actually R prime and H2. R prime and H2. So how they react is the NH2 will be the nucleophile, go and attack the COCl. The Cl is kicked out. The NH2 is going to replace it. Okay, so I should put it in this way. The nucleophile should be R prime and H with the lone pair. So this is the nucleophile. So that's why the nucleophile go and attack this carbon, right? You can see the product form is NHR prime that stick to the CO. It actually stick to the C, no? So it's NHR prime. So which is this one? Okay. Which is that? That is the nucleophile. And then the H, the extra H here, you see there are H2, right? So one of it is not there. So another extra H, right, will combine with the Cl that come out, and then they form HCl. Okay. So basically it's like this. Nucleophile plus H plus. Okay. If excess NH3 use, the HCl form is neutralized to NH4Cl. That means this product, the HCl and the HCl here, will neutralize by the ammonia to form ammonium chloride. Now, next one. The next reaction is esterification. So esterification, what we learned last time is carboxylic acid can react with alcohol to form ester plus water. Now this is slightly different. Acetylchloride react with alcohol to form ester and HCl. Okay, so we should expect something like this. The Cl and the H is taken out, and then after that the remaining join up straight away to form ester. Okay, so the one that I circle in red is taken out to form HCl, and the one that I don't circle, you just join them up, then they form ester. Reagents and conditions: aliphatic alcohol at RTP. So you can use aliphatic alcohol, that means alcohol without benzene ring. So you can use that. If you use that, RTP will be enough, room temperature and pressure will be enough. But if you use phenol, right? If you use phenol, you need to be more extreme a bit in terms of the conditions. You have to dissolve it in NaOH. Why we dissolve it in NaOH? So that it can release its H plus more easily, no? Or it can form hydroxide ion more easily, and you have to warm. Okay, so once you get ester, right? So it is possible to break down the ester through hydrolysis. So we have two types of hydrolysis. We have acidic hydrolysis or alkaline hydrolysis. So we start from acidic hydrolysis first. Ester plus water, then it will form back to the original component, which is carboxylic acid and alcohol. So where they break down, remember, they will break down at this part. The left hand side will form carboxylic acid, the right hand side will form alcohol. Okay, that is acidic hydrolysis. But if you use alkaline hydrolysis, right? So what we can say is there are two steps. The first step is same like the acidic hydrolysis, which form carboxylic acid and alcohol. The second step is carboxylic acid will neutralize. Carboxylic acid and NaOH will go through neutralizations to form salt and water. So meaning that if we are using alkaline hydrolysis, the final product is alcohol plus salt plus water. You get three products. Very similar to this one. Get three products. So very similar. And very similar in the sense that it has two stages to discuss. First stage like that, and second stage is neutralization. Okay, so we look at 9.5, relative ease of hydrolysis. So we are comparing between aryl chloride, this is chlorobenzene, and the middle one is alkyl chloride. Alkyl chloride is AS chemistry, halogenol alkane. And the third one is acyl chloride. So acyl chloride is the most reactive and the easiest to hydrolyze. As you can see just now in the notes, right? You want to do hydrolysis for acyl chloride. See the first part of the table. RTP will be enough. No need catalyst at all. One showing that this is very reactive. Very reactive. So now let's move on. Okay. Okay, we have to know how to explain it. Why acyl chloride is the most reactive, why aryl chloride is the least reactive, why alkyl chloride is moderate. Okay, let's start from here. Aryl chloride, that is the chlorobenzene, do not undergo hydrolysis at RTP because the p orbitals from chlorine, the lone pair, the lone pair from chlorine overlap with delocalized p electrons, giving the CCl bond a double bond character. Double bond character means very hard to break the CCl bond, so the Cl is hardly removed away, so OH could hardly come in, so that's why they are not reactive. So the important word here, make sure you know that the important word here is the lone pair overlap. The lone pair overlap with to form the delocalized electrons. The lone pair of lone pair from chlorine overlap with the delocalized electrons. Now the second point is about alkyl chloride. So they said require a strong alkali under reflux, and this is the AS chemistry. So you need strong alkali, you need to reflux, then hydrolysis can happen. So it's very hard to make it happen. So as carbon doesn't have a high delta positive, so they also mention out the reason. So imagine that our situation is Cl. Okay, so this carbon is not so positive. So because of that, nucleophile could hardly react with that. Not positive enough. Now, third point, acyl chloride undergo hydrolysis with neutral water at RTP. You see the changes here. Just now hydrolysis, we need strong alkali. And we need reflux. And now acyl chloride, we just need water, and we need RTP. The reagent is mild water. The condition is mild also, RTP only. So because the carbon atom is bonded to two highly electronegative atoms, which is oxygen and chlorine. So the acyl chloride, right, the carbon is bound to oxygen and chlorine, and that carbon become a high delta positive carbon. Therefore, attack by a nucleophile is much more rapid. So let's draw out this and let you imagine a bit. So Cl, we have double bond O. So this is very positive. This is very positive. Nucleophile will quickly come in and attack with it. So the nucleophile here, of course, it is the OH minus. Okay, so we still have chapter 10, carboxylic acid. This is quite short, carboxylic acid. So let's see. Carboxylic acids are weak acid and dissociate incompletely in aqueous solutions. So let's see what happened here. Carboxylic acid dissolve in water, dissociates to form the anion and the hydroxonium ions. So this is the carboxylic ion, this is the hydroxonium ion. So they form weak acid. Of course, the acid strength is better than phenol. Okay, it's better than phenol. So the OH bond in carboxylic acid is weakened by the carbonyl group C double bond O, which is this part, C double bond O, will weaken the OH group. How they weaken it? They are attracting, they are withdrawing the electrons. So imagine something like this. Okay, something like this. C double bond O, O, H, R. So withdraw the electron. So making the O not negative enough to hold the H, so that this bond is weakened. Then next point, the carboxylic ion is stabilized by the delocalization of electron around the COO minus group. COO minus group. So they are trying to say that once they form carboxylic ions, they can't remain, I mean, it doesn't remain as COO minus. Okay, but delocalization happens. The electron from the double bond there, yeah, can just freely move to this side as well. So making the double bond here can come here, and they are like moving around, So that's why they put dotted line here. The strength is like one between single bond and double bond. The strength here, single bond and double bond. And the negative charge is distributed around also. So that's why they put in between. Just now they put a negative charge here. Now they put in between already. Delocalization happen. And it also means they spread the negative charge. Okay? Spread the negative charge. So you can see the words. And it become more stable, of course. More stable. More stable means they are weaker. A weaker conjugate base. So the carboxylic ion is stabilized by the delocalization of electron around the COO minus group, spreading and reducing the density of negative charge, making it less likely to bond with H+. So they don't bond with H+ so much already, and meaning that this is a stronger acid compared to phenol. And when it's stronger, that means this is a weaker base. And this is very stable. Very stable means they remain as anion for a long time. Okay, now let's move on. 10.1 Relative acidities of carboxylic acids. So the statement there, they said acidity of carboxylic acid decreases as carbon chain length increases. Because, so what kind of information given here? Let's say if you compare between methanol acid and ethanoic acid and propanoic acid. So 1 carbon, 2 carbon, and 3 carbon. So we have to say that the 1 carbon carboxylic acid, methanoic acid, or methanol acid. Methanol acid, methanol acid, HCOOH. Methanol acid is stronger than ethanoic acid and stronger than C2H5COOH. So this is their acidity. Okay, now next point. Alkyl groups are electron donating group. Alkyl group, this one, C2H5 or CH3, these are the alkyl group. They are donating group, electron donating group, which have a positive inductive effect, which means they donate electron to the right hand side and it itself become positively charged. So C2H5 also donate electron to the right and C2H5 itself become positively having delta positive charge. So that is positive inductive effect. Increasing strength of OH. So imagine that donate electron to the right, making this O stronger, making this O more negative, and hence can attract the H strongly. Now, alkyl group increase negative charge on ions formed when dissociated. When dissociated, that means when the H plus move away. When the H plus move away, so the alkyl group make the carboxylic ions more negative and making it easier to accept the H plus and reform the molecule. So that means that explains why this is a weaker molecule. Because after H plus move away, right, the C2H5 can push a lot of electrons to this side, making this oxygen very negative, and then the H plus will easily come back and stick to the O minus just now and forming molecule again, and hence no H plus, and because of that the acidity is very low or very weak acid.